Hi, this is a continuation for Power Electronics lectures where we cover the basics of power electronics. In the previous video, we have covered buck converter, the topology, the analysis, the design, and consideration. So make sure that you have seen the previous video because there are some details will not repeated in this video when we talk about the new converter, which is the boost converter. So in the previous converter, we have covered the topology and also to derive the relation between the input and the output, we mentioned two steps. The first step is the analysis of the on-time and off-time circuits, where we find the VL, the voltage across the inductor for each case, and then derive the relation of the input-output using the voltage second balance or the capacitor charge balance, where we average the on-time circuit and off-time circuit. So in the previous video, we have seen that the buck converter has the relation of V output equals delta, which is the duty cycle, multiplied by Vn. But I think I forgot to mention that the I output as well has a relation with I input by this relation, which is 1 over delta, okay? And it's reciprocal of the voltage relation. And as we mentioned, these are the steady-state equations where we know the final value of the voltage or current in the steady state, but in the transient we need to model it using one of the modeling techniques to know what will happen in the transient. So today, instead of buck converter, we are going to see the boost converter. And again, we have an inductor, we have a switch, and we have a diode, but they swapped the places, okay? So the switch here, it's connected to ground. That's why we call it low side switch, and it needs low side driver. So we apply the PWM here on the gate. Maybe this is a Mosfet or an IGBT, and then we find a new pattern of currents and voltage. Again, to know the input and output voltage relation, we need to go through two steps. We need to know the on-time circuit and off-time circuit. We have to compute the VL, and then we use the voltage second balance to average these VLs over one period, and then we will get the total current. So let's now start with the on-time circuit, where we have that switch turning on. And when we turn on that switch, that means it will be like a short circuit because we assume it's ideal here, okay? And once we have that switch turn on, okay, that point here, I think it's the anode of that diode, it's connected to the ground. And if the anode is connected to the ground, that means it's less than the cathode. That means we have a reverse bias diode and it will be off, okay? So now this is the circuit of the on-time period. And now we see now the voltage input here is in series with the inductor, and the current coming out from the voltage source is the same as the inductor current, and that happens in the boost converter. Now, if we have this switch on, that means the current will flow from the input here, going through the inductor, and we are now charging the inductor. What will happen to the output? I think at that time, the load now here will depend on the charge of the capacitor to give it the current, and the current will be opposite to the assumed IC here in this arrow, and it will be supplying or delivering current to the output resistance. Okay, the question now, what is the voltage across the inductor in the on-time, because this is the on-time circuit. So I think to know the voltage, we have to ask ourselves what is the node at the left, and we subtract from it the voltage at the right. The voltage at the node at the left, I think, is the same as V input here, and at the right, because the switch is bringing that point to the ground, I think that this point will be 0, and VL now is V input minus 0. Now let's go to the off-time circuit, and I think again we have that switch is off, and at that time we have here voltage, okay, and at the moment we are switching off that transistor, I think we are changing the current in the inductor, okay, and that will produce some voltage across the inductor because it wants to resist the change in current. So that means that at the moment exactly where we switch off that transistor, we have here a voltage, and that voltage will be like a battery, and we have here a battery, and that is another battery. So you can imagine there are two batteries in series, okay, and both are pushing current toward that point, which forward bias this diode. we can interpret this by another way. We have that inductor already has current from the first duration here, okay, and it wants to keep that current on the same direction. That means it has to forward bias this diode, and that diode will be on. Now, what is the current flow? I think the current will go from the source, going through the inductor, through the diode, and now supplying the capacitor and also the load. Okay, so it will be separated here and then will be combined there and go to this circuit. Now, the question again, what is the voltage across this inductor? Again, the voltage at that node is the same as V input, and the voltage at that node is the same as, I believe you know it, V output. So now, off-time circuit where we have 1 minus delta T, the VL is Vin minus V out. Now, we know the voltage of the inductor, across the inductor in the on-time and off-time. I think we have to use the voltage-sec balance to integrate these two values over the times, and then we get the average value of the input and output, okay? So by using this law now, we have the on-time value and off-time value. We just average them by the same integration. So from 0 to delta T, we have V input here. And from 0 to 1 minus delta T, we have this value, and we integrate that. And after getting the result, I think you will get V output equals 1 divided by 1 minus delta V input. Okay, so this is another relation. Now, again, we have this relation, which is a steady state input-output equation. It doesn't tell us how the output voltage changed the value from one to another, but it gives us the final steady value. Now, if we assume that input power equals the output power, and there is lossless component in between, that means we can get a relation between the input current and output current, and it will be like that. And you will find it's reciprocal of the V output and V input one. So the V output equals 1 divided by 1 minus delta Vn, and here the reciprocal of that is I output equals 1 minus delta I input. And now let's continue to know the analysis of the waveforms of each part in the circuit. Okay, so we have here again that switch, and will turn on and will charge that inductor, and then will turn off, and that charge will be released the other part of the circuit. So we are expecting here a rising and falling currents like that, and this should happen if we have a balanced circuit. If the current is keep rising, that means we are going to an unstable situation. Okay, so if this is the current, what is the current in the switch, and what's the current in the diode, and also what is the voltage across the inductor? I think after we have this waveform, which is the same as I input as well, because I input and IL are in the same track here. So the voltage across the inductor, in that case, I think while we are charging, the voltage is positive because we have DIL by dt is a positive here, okay, times L, it will give a positive value. But during the discharging, we are having here a negative voltage. Okay, so what is the current of the switch? I think the switch has a current just during the turn on time, where we have the same IL current is going through that switch. So that portion now is the same as the portion we are expected going through that switch. And that portion will not be supplied by the switch because it will be off. That switch will be going, so IL will be going through the ID, the diode here, during the off time. So that portion here is the same as the portion pushed toward or through the diode. Okay, so this and this combination of these will give us the IL. Okay, so this is ID. What about IC? We know that the capacitor always passes the AC component of the waveform. Okay, so we have here ID. Okay, that ID here, okay, will be separated to IC and IR, but IC will take just the AC component of ID. So here we have ID, the current from the diode, and that will be separated to DC current, which is this value, will go to the load, and AC current or AC component, and that will be bypassed by the capacitor. So the expected value here is the same waveform but shifted or subtracted from it I output, which is the average I output, and we assume it's constant here. Okay, so this is the waveform of IC, and again we study these waveforms because it helps us to identify the power dissipation in each component here by knowing the current waveform, and we know the average or RMS value of that current or voltage, and multiply it by maybe RDS on or VCE sat or VF here, and we get the power dissipation, and we know our efficiency or converter efficiency. And as we done in the buck converter, we are looking now to identify the equation for the ripple current, because that ripple want to be maybe maintained within some limits. So the on-time equation here, we have the voltage across that L equals Vn, we got it before, and the off-time VL equals Vn minus V out. Okay, but we know VL equals L di by dt, and that di is the change in current, which is this one exactly. Okay, and that sometimes happens, that change in current happens from low to high during the on time, or from high to low during the off time. So I can really get delta IL from the on-time equation or the off-time equation. Now from the on-time equation, we know that change in current from low to high happens just during the on-time, which is delta T. And that will be Vn divided by L, which is this L, okay? Or we can get it from the off-time, and it will be like this. So we can use that equation or that equation to conclude the equation of delta IL. If I use that equation now, I will get delta IL in terms of Vn, F, and L. If I use that equation, I will get it by the output voltage as well, and I can convert that output voltage to Vn by using this equation as well. So both of them will give us the same equation. Now this is delta IL, which is the ripple of the inductor current, and that's a function of V input and function of delta and function as well of the frequency and the inductance value. And I think if we change the inductance more and more and more, this will reduce the ripple. If we increase the frequency more and more and more, this will reduce also the ripple. And you can get the value of L that maintains some ripple value if you want to design it to be within some values, and you can select and design your inductor value. But what about the capacitor? Does it have any ripple here? Let's see. If we have that current going through the capacitor here, and that current has this waveform, that means yes, the voltage will change with that current. And how the voltage will change, I think during this portion here, the current is minus, because at that portion here where the switch is on, the output now is relying on the capacitor to give it its charge. So that's why it's discharging that current like that, and that's why we have a negative value. So it discharges the value to the output resistance here, and the value is I output, and that's during just the on time of that switch. During the off time, it will get some current going from there to that capacitor, and that will be this portion here. Okay, so that one is the value of discharging, and that one is the value of charging. Okay, and now we get this ripple here for the VC, which is the output voltage, and I think that any ripple of the output voltage across the output capacitor here, it equals the charge, the difference in charge divided by the capacitance. But we don't have the charge, we have just IC, but IC is responsible for the charge by the integration. So if we done the integration of the IC here, I think we get the charge value, which is the area under this curve, and that charge will be out of the capacitor during that period and into the capacitor during that period. So what we want to know is the integration value. So the charge equals the integration of IC waveform just during the on time or the off time, because if we computed the on time charge here only, this will give us the value from there to there, okay, and which is the delta VC. And if we computed that value, it will give us the value from there to there, and that's the same as delta VC. So it's enough for us to know one of them, not both. Okay, so what is the value of the charge here, or what's the area under this curve? I think we know it because it's just a rectangle here. The distance from there to there is I output, and the distance from there to there is delta T. So it's I output delta T is the area under this current waveform. And I think by substituting these values into this equation, we get delta V output, which is the peak-to-peak voltage ripple now, equals delta I output divided by FC. Again, this has a relation with the frequency. If we increase the frequency, this ripple will be decreased, and also the capacitance. If we increase the capacitance, the ripple will be also decreased, because it will be considered as very big value, and it doesn't allow the voltage to change much. But it is also a function of the output current here. And if the output current increased more and more and more, that means it will discharge that capacitor very quickly. And that curve will be steeper here, and it will show or expose a higher ripple. And now, as we've done in the buck converter, we want to know the impact of I output on IL. Okay, so we have these two equations. It relates the V output to V input and I output to I input. But we know that I input here is the same as IL, okay? So the relation between I output and IL is the same as the relation of I output and I input, okay? So we can really use that equation just to explain what will happen. So when I output has a significant value, so the IL also will ripple across a significant value, and when I output decreases more and more and more, that also will decrease the average current of the inductor without increasing that ripple, but we will continue decreasing that until we get some boundary conditions here, and then we go to discontinuous conduction mode. So if all the values are above the zero, so it's called continuous conduction mode, and if it reaches zero, it will be called boundary conduction mode. And if it start now crossing with the zero and producing some pieces with zero value here, so that means we are in the discontinuous conduction mode. So the question now, what is the minimum value of the inductor here, just to keep us in the continuous conduction mode? And if we decrease it, so we will know that we are going to discontinuous conduction mode. Again, we have to go back to our equation, which is delta IL equation, and we start thinking of the case where we have the boundary condition. At the boundary condition before the discontinuous conduction mode, and we still in the continuous mode, we have that ripple, okay? That ripple, the minimum value of it will just equal zero, okay? So at that time, the average current of the inductor, which is that middle line now, between the maximum and minimum, will be halfway between the minimum and maximum. So I can say that the ripple current from maximum to minimum equals the IL average, okay? So that value now will equal to IL average. But what is the value of IL related to the I output? I think I output equals 1 minus delta IL from the previous slide, and I think we can get that in terms of I output, and we can get L from that equation now to be more than delta 1 minus delta V input divided by 2F I output average. So if I output now has a value, I have to use that I output. If I want to maintain my boost converter to be in continuous mode, for example, if it supplies 1 ampere, so I have to choose L to sustain that. And that relation, if you know the V input, if you know the delta and I output, but if you want this relation to be in terms of the value of the output resistance or the load resistance, so just you can convert the V input by knowing the relation between V input and V output, and also I output, and you can get this relation. So you can use that relation, or you can use that relation according to what is given to you. And again, if we have discontinuous conduction mode, does this relation still valid? V output equals 1 divided by 1 minus delta Vn. The answer is no. And we have to derive again with the discontinuous conduction mode, but you will get a relation like that, and I think it's squaring here and squaring there. It's non-linear, and it has I output there, and it is load dependent. Now we have something called parasitic inductance and capacitance, and its impact on the boost converter. We have these parasitics, I mean the inductance and capacitance, and also the resistance appearing in the other components like inductors and capacitors. We have this relation, which is V output equals 1 divided by 1 minus delta Vn. And I think if delta is 1, so I will have 1 divided by 0. And 1 divided by 0, that means infinity. Theoretically, I should get infinity voltage. And that's practically will not happen because of the parasitic inductance and capacitance in the circuit. So it will limit the output value and will not accepting any value from this relation. And the practical effect will be like this. So when you increase more and more delta, yes, you will get more voltage at the output, but at some point you will not get any more, and the output will start to drop because of the parasitic inductance and capacitance. And if you look at the efficiency of this converter is good in if the delta is small, okay, maybe below 0.5, and after 0.5 it will start decreasing more and more, and it will not be acceptable. So actually, practically, in practice, boost converter are not operated beyond a duty cycle of 0.7, and usually they choose below 0.7 or below 0.5 to make sure that it has good efficiency and we are within the practical relation of V output and V input. And that brings me to the end of this lecture. I hope you got a good overview about boost converter, and it's good you see the buck converter because we have spoken about consideration for the buck converter, which is also relevant to the boost converter topic. So thank you very much and see you in the coming video.